Today's session, we'll be covering greedy and like a little bit of sorting, but pretty much mostly greedy. Um, so this is the agenda. So we'll talk about greedy, then we'll do a couple problems, and then just like close it out as usual. Yeah, so what is greedy? So if you've heard of greedy before, you've probably heard of this phrasing that greedy will make locally optimal choices which yield a globally optimal solution, right? So a greedy algorithm is a kind of strategy or algorithmic technique which is used to solve optimization problems, right? So minimum or maximum problems. And it has this special property called the greedy choice property, which says that we're able to make a decision and then we never have to reconsider the choices we've made in the past, right? So what this means is that we're able to kind of deal with the input as we go, and we never have to like rethink the current solution that we're building at any moment, right? So this is kind of abstract, but all this to say that greedy algorithms itself are generally intuitive in that what is greedy about them is kind of natural for us to think about, right? So I think it's important to draw this distinction between greedy algorithms and dynamic programming algorithms. So oftentimes when a greedy algorithm fails is when a dynamic programming algorithm succeeds, right? But there are also many times where a greedy algorithm can be used, like they both can be used to solve the same problem. And in those cases, usually the greedy approach is faster or it saves more space. And so the major difference here is that in a problem that can only be solved using dynamic programming, the power of dynamic programming comes with the fact that we've stored all the past solutions. And so to solve the current subproblem, we're able to draw upon those solutions, and then we're able to proceed that way. Whereas for greedy, we don't have that. We don't necessarily have that information, and we don't even need that information is basically the idea, right? We can just kind of solve the problem as we go, right? Yeah, so yeah, it will like leave all the options on the table, right? When we're building a solution to like the current subproblem, we'll kind of remember all the past to help us compute the current thing, and that's dynamic programming. And so now why is sorting a part of this at all? And so oftentimes, right, the structure of the problem is not immediately obvious, but then after you manipulate the input via sorting, then sometimes the greedy structure will like show itself a little bit, and then we can kind of take advantage of that from there, right? And obviously, this only makes sense when we can actually manipulate the input, right? So there's some greedy problems, right? We're not able to actually just sort the input. So sometimes it doesn't make sense to do any sort of sorting. Yeah. So that's like the spiel on greedy. It's like kind of hard to grasp if you've never seen it before, but we'll do some example problems and then that'll become clear. But any questions on like this so far? Cool. All right. So that goes into our first problem. It's called the jumping game. And so you're given an array of integers, and each entry represents the max length you're able to jump from that position, right? So each position has a number, and then it tells you the max distance you can jump from that cell. And so starting at the first entry, the question is, what is the minimum number of jumps required to reach the last index, right? So you can think of this as like each entry has like a springboard with a certain like power scale, which tells you how far you can jump, and you're able to jump like any distance in between, right? And so any questions about the problem statement? Let me just like take a second to kind of let it sink in a little bit.
Wait, so if it says 2, does that mean are you allowed to jump 1?
Yeah, you're allowed to jump 1.
Oh, nice. Yeah.
You're also allowed to jump 2. Yeah.
Okay.
Yeah, exactly. Yeah, so yeah, so all all the numbers are integers and they're all positive. The other thing, yeah, so this is slightly minor, but also kind of important, is that there's assumption that it's feasible in that like we're actually able to reach the end. So that's kind of a small point. Yeah, so here's the example, right? So this is the first position 2, right? And so we're able to jump to either 3 or 1, right? And we have that option, right? And so let's just suppose that we jump to 1, right? Then that means that we can only jump like forward once. So we go 1, and then we're at 1 again. So that's the only jump we can do, right? So that was like one example of reaching the last element of the array, but it's not the optimal, right? It's not the optimal choice, right? The optimal choice will be jump to 3 and then jump directly to 4, right? Because we have that ability, right? 1, 2, 3, right? We can just jump over all these elements and reach 4, right? So this is kind of a pretty good example that maybe gives you some ideas about kind of what we can possibly do, right? So this is kind of the first greedy idea would be, okay, let's every time we just jump as far as we can, right? And we've already kind of seen that this doesn't work, right? Because, right, if we jump as far as we can, we jump over the 3 and go to 1 and go to 1 and 4, and we have a suboptimal solution, right? So jumping as far as possible doesn't work, right? So there's something special about jumping to 3 and not jumping over 3, right? That we need to kind of take into account, right? And so if we kind of think of each entry as some like amount of distance that can be covered, right? We kind of want to pick the elements which will maximize the distance, right? So altogether, the locations we jump to should ideally be pretty far, right? So this actually kind of summarizes a greedy idea. So like with the notion that the previous greedy idea didn't work, and like this kind of statement, maybe we can kind of develop a second greedy idea. So I'll like let you all think about it for a second. Like someone can propose a potential like greedy strategy.
So within the range, could we find the largest number within that range and then use that to jump?
Yeah, so yeah, that's pretty good. I don't know if that, I'm not sure actually if it might not necessarily be the largest number, but
I have an idea.
yeah, go for it.
So what if you like looked at all the index, so let's say you can jump like 1 to n number of spaces.
Mm-hmm.
So you look at all the indexes 1 to n, and then you see if the length from jumping, like if I jumped one spot and then the length that I would be able to jump the next time is bigger than if I jumped the max length and then the next length. So you could see if like jumping a shorter distance would be like better for you in the next step.
Gotcha. Yeah, I think that's pretty much the idea, right? And so to kind of summarize that intuition, is we have this like jump to the location which will let us jump the furthest, right? So I think that was pretty much what you're saying, right? So this location might not necessarily be the best location like in the available spots we can jump to, but it says that, okay, if we go to this location, we can actually go further than if we went to any other location, right? Still
Yeah,
costing
right.
only one jump, right?
Mm-hmm.
Yeah. So we're kind of maximizing the potential furthest distance that can be traveled, right? And this is like pretty intuitive to think about, right? If you're like maybe playing this game as a real person, maybe right, that's probably the choices you would make, right? After maybe a few rounds of this game, you would realize that's a great strategy, right? yeah, so this is kind of the idea, right? We jump to 3, which allows us to jump further than jumping to 1, right? So that's kind of summarizes, that captures that idea, right? So now the question is, okay, when do we decide that we've actually made a jump? And I think we've kind of addressed this already, right? And the idea, I think the idea was just that we're at some location, and then we just check all the entries we can jump to, and then we jump to the entry which allows us to jump to the furthest, and we increment jump, and then we repeat like that, right? So that was pretty much the idea. And there's actually nothing wrong with this solution, and I like it a lot. It's very easy to understand. And I'm pretty confident that it also like runs in the best runtime. But there's a much cleaner way to kind of do this algorithm that will make the code a lot simpler, right? So let's kind of investigate that a little bit. Yeah, so let's say we're at let's say we're at 2, right? And so we're able to jump to 3 and 1, right? So using the kind of idea and algorithm that we had just encountered, right? We would go to 3, and then we would check like 1, 5, and 4, right? And then we would be done because we could reach the end. But so like what's like slightly suboptimal about doing it like this, and what is redundant, and what can we kind of, how could we try to fix that?
Well, with the idea you mentioned of jumping to the one that lets you go the furthest spaces, wouldn't that make you go from the 3 to the 5 first? Or would you have like a base case where if you can reach the end, you go?
Oh yeah, so maybe let's just like let the array extend as far as possible. And, like, don't worry about this being the end here, but just kind of focus on like this initial part where we're at 2, then we've decided to jump to 3, and now we're checking like the next 3 elements.
I got you.
Well, you're checking how far you can go from 1 twice when you do that.
Exactly, right. And right, so kind of the moral of the story is that we don't need to pretend that 1 is like, after we've jumped from 2 to 3, we don't need to pretend that 1 is suddenly like still a valid option anymore, right? If we could have jumped there when we were at 2, then we would have done it instead of like going from 3 to 1, right? Right. So there's kind of some redundancy here in checking the 1 location twice, right? Because with the previous algorithm, we'll check it once on the 2, and then we'll check it once on the 3, right? And with bigger numbers, this could potentially be like a bigger issue, right? Actually, I kind of stand by the idea that it's not going to affect the runtime, but haven't thought about that much in depth, right? So yeah, so the idea is like, we only consider locations that are unreachable from the source, right? There's no reason to consider the same entry more than once, because we would have jumped there if we could have, right? Or if it made sense to jump there, right? Yeah, so that's pretty much like the slight optimization we can make. And so these are kind of like the need to knows in order to implement that, right? So of course we need to know the number of jumps, right? Because that's the return. Then the second thing is we need to know like what is the max distance that can currently be jumped to, right? Like the max position we can reach. And then, oh, maybe I duplicated that a little bit. The furthest position that we can reach, and so this is the second one is the current max distance, right? So we keep some running track of like the max distance that we've seen so far as we're iterating over elements. And then we also need this kind of more fixed idea of what is the furthest position we can reach at the moment, right? So any questions? I mean, this might be unclear since you might not necessarily know what the algorithm is, but if you can kind of like, maybe it's good practice to try to justify what an algorithm might look like with these 3 pieces of information. Yeah, any questions so far before we get into the like code? Nice. Yeah. So this is going to be the idea, right? So we have just like some base case stuff, right? And then we just initialize all these things. So number of jumps is the number of jumps, right? And that's what we return at the end. Max distance and then current jump limit, right? So we go from 0 to n, right? And we always just keep a running track of the max distance possible, right? And so we just take the max between the current max distance and I plus nums I, right? So this is the furthest distance you can travel from location I, right? And then the main body of the code says if the current jump limit is the same as the current position that we're looking at, then that means we've reached the limit, right? We've gone as far as we can, so we have no choice, but we need to jump, right? We have to decide to jump. So we change the current jump limit to whatever was the max distance so far, right? Because like we said before, right, we'll only ever travel to the location that will serve us the best utility, right, which will be the max distance. And we're also increment number of jumps, right? So we don't decide where to jump until we've seen everything that we could possibly jump to. And then we increment number of jumps and update the current jump limit. And then we just have this last check, which says, okay, if the max distance, right, or aka the current jump limit is greater than or equal to n minus 1, then we know that we can reach the end from here, so we can return the number of jumps, right? So this is like kind of the idea. It's like, I think some people call it like a lazy jump, where we don't jump until we've seen everything, and then we're able to just kind of continue looking at the array, right, without kind of backtracking to see the other elements, right? So there's no redundancy here. Another thing you'll notice is like it seems almost strange that we don't return number of jumps plus 1, because you need a jump to reach the end, right? And that's because we automatically get 1 jump because current jump limit is 0 and I starts at 0, right? So we kind of serve that last jump by just by having it at the very beginning, right? And I think if you play around with the initialization values, you could get to a scheme where you return number of jumps plus 1, and that makes total sense, right? So any questions about the idea of the code? We kind of avoid that redundancy that we talked about before. Yeah, and so why did we go through that maybe more complicated idea? Well, it makes the runtime really easy to analyze, right? So we have complexity analysis. So any runtime ideas, space complexity ideas?
Big O of n.
Yep. And yeah, so we can see we have the for loop, right, that iterates over n elements. Pretty much everything else is a constant operation, right? We have nothing fancy is going on here, right? And the other scheme, you might have to do a little bit more work to figure out the runtime, but I'm pretty sure it's also O of n. Yeah, and then the space, the space is also, we're not keeping track of any sort of array or anything, so yeah, we get a pretty clean run in space-time analysis. So yeah, I think this is a pretty good problem. It like kind of captures a lot of the greedy ideas, which is like very locally optimal choices, right? And like we never, like we don't even remember where we jumped from necessarily, right? We only ever keep track of the max distance we can jump to, and whatever the current jump limit is, right? Right. So I think that's pretty cool. Any questions or any comments on the ideas, solutions? All right. Yeah, so we'll jump into the next problem, which is meeting scheduler. So you're given an array of meeting times, and so each meeting has a start and end time, and the task is to find the minimum number of rooms needed to schedule all the meetings, right? So I think it's actually a pretty real problem. So say if you were like working for the Edge or something, and you had to schedule like meetings that students were like asking for, right? Maybe in some certain setting, it's a good idea to use only the minimum number of rooms possible, right? Yeah, so I actually like this problem a lot. Any questions? Any questions about it? Yeah, so I think there's like there's maybe like a little bit of lack of clarity here. So one thing is that the start times always come before the end times. That's just maybe like an assumption that we've already had, but all the times are integers. And then last thing is that the meetings are not allowed to overlap, right? So if we assign 2 meetings to a room, they're not allowed to overlap, but they are allowed to touch in the sense that one can end at the same time another one starts, right? And we'll see. Yeah, so these are kind of like maybe some questions you could ask. Right, so this is an example. So we have 3 meetings here, 0 to 20, 5 to 10, 10 to 20, right? So these are just like time intervals, right? And it's not hard to see that, yeah, the minimum number of rooms needed is 2, right? And we can reason this because 0 to 20 conflicts with all the other meetings, right? So it needs its own meeting room. And then we're able to schedule 5, 10, and 10, 20 in the same meeting room, right? Since they don't overlap, right? So in that sense, the answer is 2. And actually, if we kind of stare at this example more, we'll realize that no matter what scheme we decide to schedule these meetings in, as long as we put a meeting in, if it fits, like we'll always get 2, right? Like no matter like which meeting we process first, or like what kind of way we decide a meeting goes to a room, like as long as we schedule a meeting, if it fits in the room, right, then we'll always get 2, right? So this example is like not helpful at all in that sense because it doesn't really tell us anything about the problem, right? So we kind of need a better example, right? That kind of explains that, like shows some of the complexity of the problem, right? So here we have this example, right? So we have meeting 0, 5, 10, 20, 0, 10, and 5, 15. So this is one potential way you could schedule these meetings, right? So we have 0, 5, and 10, 20 in one room. We have 0, 10 in one room, and then 5 and 15 in another room, and that gives us three meeting rooms in total, right? But again, this is not the optimal solution, right? Because right, we see that the 0 and 5 could be paired with a 5 and 15. Likewise, a 10, 20 could be paired with a 0 and 10, and we could actually use 2 rooms, right? So this kind of shows a little bit more of the nuance in the problem, right? Because clearly, if you aren't smart about the way that you are scheduling these meetings, you could very easily run into a situation where you're using a suboptimal number of rooms, right? Yeah, and so what else does this kind of example tell us? Well, it tells us that the solution has to be somewhat constructive, right? It needs to, we need to actually know information about each of the rooms in order to determine like a potential like minimum number of rooms, right? So that's kind of a important point. Right. So we might actually have to try and like build out what the solution looks like, or like what the schedule might be, right? That's like an option that's on the table. Right, so so the major question is, how do we process the meetings, right? So we want to process each meeting in such a way that it makes the problem simpler and easier to handle. And like we kind of have this fact that no matter what, like all meetings will get scheduled, so we don't have to like decide to throw out a meeting or anything. But the major question is like which ones should be scheduled first and like where should they go, right? So let's just kind of address this first part, right, which is like in what ordering should we process the meetings, right? And so maybe I've kind of like set this up so that you might know the answer, but like try to think about it like from the perspective of an actual meeting scheduler, right? Like what meetings would you consider first, right? I mean, you just like even think about like your day-to-day schedule, like what meetings do you consider first, like when you have a schedule?
Well, I think you'd want to consider your first meeting first.
Yeah, right. That's kind of the idea, right? We like there's some there was kind of some feeling that okay, maybe if we schedule meetings that start earlier, right, then maybe that's like more helpful, right? And yeah, so that's kind of this sorting the meetings by the start times, right? So algorithmically, why is this an intuitive option? Well, if we process the meetings by the start times, right, then we know that whenever we look at a new meeting, it starts later than all the previous meetings, right? And that's actually pretty important because now there's no situation where we can put a meeting before, like earlier in a schedule, right? Like we always put meetings at the end of a current schedule. So in that sense, this actually this kind of idea of sorting by the start time makes sense. Yeah, exactly. Yeah, consider the ones that start first, right? Yeah. Yeah, so this is actually like a really good start already. And so now the question is, okay, where do we send a meeting, right? So we're trying to schedule a meeting to a room, and the question is like, where should we send a meeting, right? So we have some rooms already. The rooms have some meetings in them, and now we're considering some meeting, and we're trying to decide where to send it, right? And so any arbitrary room doesn't work, right? As we've seen before in that example, we can't just pick a random room and then send the meeting there. It might not work. And so like in order to kind of reason through this, we can think about the possible cases, right, that could happen whenever we're looking at a new meeting, right? So what are like some potential possibilities?
Well, you could have a meeting that finished, so you'd be able to like put that meeting in that room, or you'd have to put it in a new room.
Yeah. So you kind of hit like basically everything, right? Yeah, we could have a situation where the current meeting conflicts with all the other meetings that are in the rooms currently, right? In which case we need to call upon a new room, right? And there's also the situation where it could fit, right? So I kind of highlighted these three scenarios with the goal to like push you towards thinking like a certain way. But so the 0 rooms available says that the current meeting conflicts with everything. 1 room available means that there's only 1 location we can put this meeting in, and then greater than 1 room available means that we can put this meeting in a few different locations, right? So now the question is, okay, I've case them in this way, but ultimately there is like the choices are restricted by some, like the cases are restricted by some feature of the meeting rooms, right? So the question is what is that feature, like characteristic of like the current room? The question is like why would a meeting not fit in one room but fit in another?
Based on the end time of the room you're looking at.
Yeah, exactly, right. So each room has a meeting, and each meeting has an end time. So we can only schedule a new meeting if it if it doesn't conflict with the end times, right? Exactly, right. Yeah. So it's restricted by the current end time of a given room, right? So we kind of have these two pieces of information, right? So we process the meetings in order of the start times, and we'll schedule a meeting to the room with the earliest end time, right? And this kind of is the idea that like in a situation where we have one, where we can only assign a meeting to one room, right? That room has the earliest end time, right? So like what's kind of the major efficiency bonus we get with scheduling a meeting to the room with the earliest end time? And I mean, maybe you've already thought about this. So yeah, so I guess like this observation was like kind of simple, and we've may or may not have already made that note, but basically like for every room, we only need to remember the end time, right? There's like no other information about the room that is helpful to us when scheduling a meeting, right? So now the question is, okay, what data structure supports this really efficiently? Kind of like all these points.
Would it be a map?
A map. So why a map?
Okay, I'm not sure if I understand it completely, but I was thinking like, well, you're just trying to get the end time of a room
Mm-hmm.
based on the room, right?
Right. Yeah, but
Well,
so there's this kind of like there's this idea that if we're able to schedule a room to the earliest end, so if we're able to schedule a meeting, then we're able to schedule it to the one with the earliest end time, right?
Yeah. So if you're only recording the current end time, couldn't you just use an array since it's only one value?
But you could have multiple rooms, right?
Right, or an array
list.
list.
Okay, I think we're getting closer, maybe through process of elimination. But so the idea is we want to efficiently know what the earliest end time is, right?
What? So, I'm sorry.
So we need to like be able to get the minimum quickly.
Yeah, that's like one way to put it.
So priority queue.
Yeah, so priority queue is the
Okay.
money answer. Yeah, and so yeah, I think we've kind of like went through the thought process of why this makes sense, right? Right, because so if a meeting conflicts with the earliest end time, then automatically we have to schedule a new room, right? There's like kind of there's no other way to go about it, right? But if it doesn't, then we're able to fit that meeting in, right? So knowing the earliest end time efficiently is pretty helpful, right? So now I claim like this is pretty much like all you need to know to write up the algorithm, right? So like kind of does anyone want to like venture like what the algorithm looks like, or like what we might want to return, kind of the structure?
of like how we can like look at each meeting room and decide whether we need to add it to the queue or whether we can just alter an existing thing
Yeah,
in the
like
queue?
what would be the like series of steps? Yeah.
Well, so what you do is you'll start by putting, I mean, it would be helpful if you had a way to sort the meetings
Yes.
out
Yeah. So we can sort the meetings at the very beginning. Yeah.
based on start time. Okay, yeah. So assuming that you start with all the meetings sorted, you can just start by adding one. And then what you can check is when you look at the other meetings, you can check and see if you're going to look at the first meeting in the priority queue because it has the earliest end time. And you see if the start time of that meeting is, if it's greater than or equal to, then you can just push the meet, then you can just schedule it. Otherwise you have to make another meeting.
Yeah, so that's pretty much the high level idea. And there's still some kind of implementation details that are a little bit unclear. But yeah, so sort the meetings by the start time and initialize the min heap priority queue. Then for each meeting, we'll remove the first element from the priority queue only if the current meeting starts after this end time, right? And then we can just add the end time of the current meeting to the priority queue, right? And we basically get all the information for free, and the answer is the size of the priority queue, right? So got any questions about the ideas? I'll like show some of the code, and then I think the code might be helpful too. But
Wait, what do you mean by current meeting? If current meeting starts, like, what's that referring to?
Yeah, so basically we're iterating over the meetings, and so
okay.
like at
So
each iteration, we're looking at like one specific meeting.
Okay.
Right? But we also have the first element from the priority queue gives us the earliest end time, so we can kind of compare these two elements. Yeah, so this is like a pretty smooth algorithm, I would say. But here's the code. So room end times is the priority queue, and then this is the sorting function. Yeah, so this kind of goes into like a point that I'll make later about being familiar with how to sort, but this is a fancy and slick way to sort using Java. So this is a lambda function, right? So A, B are the parameters, and then the output is A0 minus B0, right? Which is the difference in the start time. So if it's negative, then that means that A comes before B. If it's positive, that means A comes after B, right? And so this is like one very easy way we can sort an array of arrays, right? So these kind of like short techniques can like save you a lot of time and a lot of errors in your code if you're familiar with them. Right, and so now we iterate through each meeting, right? Using a for each loop. And so basically we need to just kind of check the size of the priority queue just to make sure we don't do any errors. But once we do that, then we can check if the start time of the meeting is greater than or equal to the earliest end time, right? And if it is, then we can remove, right? And no matter what, we'll add the end time of this current meeting to the priority queue, and then we can return the size, right? So if we check on each iteration, we're always adding, but on some iterations, we're also removing, right? And so at any given point, we have knowledge of all the end times, right? But the most important piece of information is that earliest end time, right? So yeah, so like questions and or swings of the complexity analysis. I think this one might feel a little bit more tricky since not all the operations are constant operations, so we need to keep that in mind. Yep. Yeah, we got a guess for the, or not a guess, I mean, it's the right answer. N log n for the sorting, right? So that's going to dominate the runtime, right? And right, no matter how long the stuff takes, like none of it's going to exceed n log n, right, for the sorting. So that's spot on for the sorting. The space is also kind of interesting too. Like what would the space be for this?
Would it just be O of n as the
Yeah.
worst case?
Yeah, it's the worst case, exactly right. If all the meetings conflict, unfortunately, we have no choice. Yeah, so n log n and O of n space. Yeah, so I think like if you want, you could say like this is O of k space, where k is like the minimum number of meeting rooms we need. But yeah, that's certainly bounded by n. And then all these priority queue operations, right, take no more than log n time, right? So none of these operations actually affect the runtime. Yeah, so kind of this sorting procedure, right? So basically, in Java, you can pass like an array. You would pass an array into the sorting, right? And then you usually pass a comparator, right? So some class which can compare two elements of the given array, right? So this is kind of like a very like shorthand way to do the sorting, right? But so the comparator takes in two elements, A and B, right, which are elements from the array, and then it returns -1, or it returns negative if A comes before B, positive if A comes after B, 0 if A and B are like the same, right? So that's all the information that the sorting algorithm needs, right? It just needs to know how to compare two elements. So we just say that this is how we should compare any two meetings, just by their start time, right? So we can do A0 minus B0, and that will tell us which meeting comes first, right? If we made this, if we like flip these and we did B0 minus A0, it would schedule the meetings in like decreasing meeting times, decreasing meeting start times, right? Which is not what we want, but yeah. So kind of like the wrap for greedy and sorting. And I mean, in general, like we can try to think and apply the like any sort of situation to a real life scenario, and then oftentimes that like makes the greedy choice like a little bit more apparent. And I would say like sometimes the code is usually simpler than the ideas, right? Maybe if you're familiar with sorting, it will be simpler. And yeah, the next thing is just like be comfortable using the data structures, right? So like if maybe you're rusty on the priority queue, like just be ready to use like any of those sort of data structures to kind of help assist you in the greedy strategy, right? Yeah, so here's some other problems. I actually really like all of these problems. I think these are like definitely like really awesome, cool problems, and they use a lot of the ideas that we've gone over in the past. So I think like knowing that these are greedy problems, I don't think will necessarily make the problem any easier for you actually. So in that sense, these are great problems. Yeah, so I would try all of them at some point, even just for fun. But yeah, so that is a wrap on the greedy algorithms. Thank you, everyone.
That's fantastic. Thanks so much, Dorian.
Just under 45 minutes.